Question 5 from the thermochemistry checkpoint. So this was the checkpoint for the entire module. We see iron can be extracted from iron oxide, iron 3 oxide, using the following oxidation reaction with carbon. And they give us the heat of this reaction. The delta H of this reaction is 467.9 kilojoules. How much heat in kilojoules is needed to convert 292 grams of iron 3 oxide into pure iron? And then they give us the opposite side. They say, okay, if we add this much energy to the reaction, right, in the presence of iron 3 oxide and carbon, how many kilograms of iron can be produced? So kind of two different versions of the same question. So for part 1, we want to convert mass into moles and then use the molar coefficients in this thermochemical equation to convert moles into energy. So for part 1, I've got 292 grams of iron 3 oxide. I go and look up the molar mass of iron 3 oxide, and it's approximately 159.7 grams per 1 mole. So we can go and see 292 divided by 159.7. Got approximately 1.828 moles of iron 3 oxide in this reaction. The balanced thermochemical equation tells us for every 2 moles in the reaction, that's the energy we release, right? So we want to go from moles now. Okay, 2 moles in the reaction of iron 3 oxide are going to require, it's an endothermic reaction, 467.9 kilojoules of energy. So multiply by 467.9 over 2, and we see that it's going to require about 428 kilojoules of energy for this reaction. Question 2 is going to be very similar, except for now we're going to start with energy. So I've got 6.5 times 10 to the 7 kilojoules of energy. How many kilograms of iron? Well, we know now we want to do this reaction for iron. So that's what we want to find, is how much iron can we make from this reaction. So the balanced chemical equation, the thermochemical equation, tells us for every 4 moles of iron we have in the reaction, we're going to require 467.9 kilojoules of energy. That's going to let us get to moles of iron, and then we can use the molar mass to get to grams of iron, and then eventually kilograms of iron. So 6.5 times 10 to the 7. Then I'm going to multiply that by 4 moles of iron over 467.9 kilojoules per mole to get approximately 5.557 times 10 to the 5. Now be careful with units, right? Kilojoules cancel out. Moles of iron. We go to the periodic table, look up the molar mass of iron. For every 1 mole of iron that we've got, we need to have 55 grams of iron. So now moles are going to cancel out. We're going to have grams of iron, so multiply that by 55. And I get 3.05 times 10 to the 7 grams of iron. The last step, because they're looking for this answer in kilograms, is just to do a unit conversion from grams to kilograms. So 3.05 times 10 to the 7 grams of iron. I know that I need 1,000 grams of iron in 1 kilogram. So we divide that by 1,000, basically subtracting 3 from the exponent, and we're going to be left with about 3.06 times 10 to the 4 kilograms of iron. I would say 3 significant figures based on our initial energy was 3 significant figures. The number came out to be 3.056, so I would round that up to 3.06 times 10 to the 4 kilograms of iron, or 3.06 E4 kilograms of iron for this problem.